So in that last mini movie, we effectively came up with the mechanism of that reaction of AX plus B going to BX plus A. We said that the reaction is going to happen at that atomic level by molecules of AX slamming into something, and if that collision is of sufficient energy, starting to break that AX bond. But that's it, unless there's a molecule of B around that, as that AX bond is breaking, it can snag on to the X. That's a one-step process. Okay, and so some reactions happen as one-step mechanisms, go from the reactant straight to the products. A real-life example of such, and you can recognize the AX and B motif here, CH3Br, so that is a alkyl halide, plus cyanide. Cyanide comes in and displaces the Br. There's a pretty little picture of the structures there. And the rate of this reaction, if it is a one-step reaction, has to be K times the concentration of CH3Br times the concentration of Cn-. Using our analogies, you've got to have the CH3Br's got to bang into something so that that CBr bond is starting to break, and as it's starting to break, the Cn is going to come on in and bond to the carbon. One nice step. But you can also have reactions that take place in multiple numbers of steps. Thus, for example, a very similar reaction here, and you'll be studying these in about a month with Joel, is same reaction. Okay, we've got a carbon bonded to a Br, reacting with the cyanide. Going to the cyanide has now come in bonded to the carbon, and the Br is all by itself. Right? But this goes in two steps, because this thing that's attached to the bromide right here is a big bulky group. Okay, so the first step of this reaction is that this molecule bangs into something, okay, get enough energy, it can break the bond, and so the Br- goes off, leaving this cation behind. Okay, but this is a whole step. It's not like here, whereas the carbon-bromine bond is breaking, the cyanide sneaks in. In this first step, the carbon-bromide bond completely breaks. And then in the second step, this cation that was formed in the first step and can be floating around all by itself doesn't need the bromide or the cyanide there immediately. It can make itself float around, and then it will grab the cyanide to make the final product. Okay, two steps for this reaction compared to one step there. And hopefully you're happy about the difference between those two different mechanisms. Now, when we have a mechanism that consists of more than one step, it brings in quite a few complicating factors. So it's worth spending a teeny bit of time on that right now. So first of all, if you've got multiple steps in a reaction mechanism, rule number one is that those steps must add up to the overall reaction. Otherwise, it's not a valid mechanism. Oh, and here, let's look at it. First step, you got CH3 3 times CBr. Well, that's one of the reactants in the original reactions. That's good. And that's doing something to give us this CH3 3 times C+. I don't know what that is, but we also get Br-, which is one of the products of the reaction. Now then, that CH3 3C+ comes in step 2, combines, reacts with the other reactant of the reaction to make the other product. Okay, so if we add these two things together, these two steps together, then the CH3 3 times C+ that was made in the first step gets used up again in the second step, so we can cancel that out. And what we're left with is indeed the original reaction. If it hadn't been, the mechanism is wrong. Now that CH3 3 times C+ is called an intermediate. An intermediate is something in a reaction mechanism that is made and then used up in a later step. So in other words, it's a product of one step, a reactant in the second step. Rule number 2 says that each step must be balanced elementary reaction. Now balanced is easy, but look at that, it's all balanced, and that one's balanced. The elementary means they are one-step processes themselves. They don't have their own little multi-step mechanism. But if, for example, step 1, it's a one step, you just break the carbon-bromine bond. Step number 2, this intermediate comes together with that anion, slaps together to makes the product. Okay, one step here, elementary, one step here, elementary. Now each of those steps must be unimolecular or bimolecular, and the uni and the bi refer to the number of particles involved as reactants. So in step number 1, there's one particle involved as a reactant. The CH3 CBr has just got to smack into something, have a collision. If that collision is sufficient energy, then it will break the bond. That's the end of that step. Step number 2 is bimolecular. There you're going to have two particles floating around with each other. They've both got to be in the same place at the right time. You have to have a little bit of adjustment of geometry, blah, 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 blah. And so that is a bimolecular step. You can have, if you're really weird under peculiar conditions, so-called termolecular steps. That's where there are 3 reactant particles in a simple elementary step. But those are extremely rare, and you can appreciate why. I mean, just our 2-step, we're saying we got to have this one particle doing something and the other particle's got to be right there in the right place at the right time. Imagine the possibility of having 2 particles in the right place at the right time to go with that third particle that is doing something. So 3 important steps associated with any reaction mechanism must add up to the overall reaction, must be a balanced elementary reaction, and each step must be unimolecular or bimolecular.